Good morning, sir and classmates. I am Genesis S. Torres from Math 2B, and I'm going to discuss the 2.5 application of matrix operation in Chapter 2. Let's start. 2.5 Application of matrix operation. Stochastic matrices. Many types of application involve a finite set of A states. S sub 1, S sub 2 to S sub n of a given population. For instance, residents of the city may live downtown or in the suburbs. Voters may vote Democrat, Republican, or a third party. Soft drink consumers may buy Coca-Cola, Pepsi-Cola, and another brand. This is the continuation of stochastic matrices. The probability that a member of a population will change from jth state to the ith state is presented by a number, the probability of I sub j, where a probability of two properties should be 1 and also it satisfies all the rules of probability that it lies between 0 and 1. It can never exceed 1, it can never go beyond 0, it can be fractional or decimal. So, we have an example here of stochastic matrix, and remember, if there is a from on the top and 2 at the right bottom, you will vertically add those number. And if the 2 is at the top and the from is in the bottom left, that means you will add the given horizontally. P is called the matrix of transition probabilities because it gives the probabilities of each possible type of transition or change within the population. At each transition, each member in a given state must either stay in that state or change to another state. For probabilities, this means that the sum of the entries in any column of P is 1. For instance, in the first column we have P sub 11 plus P sub 21 plus P sub n1 is 1. In general, such a matrix is called stochastic. The term stochastic means regarding conjecture. That is, an n by n matrix P is called a stochastic matrix if each entry is a number between 0 and 1 and each column of P adds up to 1. Example 1. Examples of stochastic matrices and non-stochastic matrices. The matrices in port A and B are stochastic, but the matrix in port C is not. Why? Nevertheless, if we're going to put the from at the top and 2 at the bottom right, so from A to A, from A to B, and from A to C, then you can see that the probability matrix is stochastic if all the numbers or all the elements in the vertical direction add up to 1. So in the part A, 1 plus 0 plus 0 add up to 1. 0 plus 1 plus 0 add up to 1. And 0 plus 0 plus 1 add up to 1. While in part B is 1/2 plus 1/4 plus 1/4 is 1. 1/3 plus 0 plus 2/3 is 1. 1/4 plus 3/4 plus 0 is 1. So if we go into vertical direction and the elements values add up to 1, then the matrix is stochastic and that is important. While in part C, We use the same process by adding them vertically. Point 1 plus point 2 plus point 3 is not equal to 1. Point 2 plus point 4 plus point 3 is not equal to 1, and point 3 plus point 4 plus point 5 is not equal to 1. So meaning this is not stochastic matrix, and we cannot use this to get the right result. Example 2, a consumer preference model. Two competing companies offer cable television service to a city of 100,000 households. The changes in cable subscription each year are shown in Figure 2.1. Company A has 70% are retained, 20% switches to B, and 10% to no cable television. But Company B has 80% are retained, 15% switches to A, and 5% to no cable television. And in no cable television, has 70% are retained, 15% switches to A, and 15% to Company B. If a current company has 15,000 subscribers and Company B has 20,000 subscribers, and the question is, how many will each company has 1 year from now? How many after 3 years? 5 years, and 10 years. And if this is the case, what is the steady state? So let us answer these three questions using the stochastic matrix and matrix operation. Company A has 70% are retained, 20% switches to B, and 10% to no cable television. But Company B has 80% are retained, 15% switches to A, and 5% to no cable television. And in no cable television, 70% are retained, 15% switches to A, and 15% to Company B. So using this, let us prepare model a tree diagram so that we can use the transition matrix for the problem. So let us prepare a model like this. So the diagram shows that Company A has 70% are retained, 20% switches to B, and 10% to no cable television. But Company B has 80% are retained, 15% switches to A, and 5% to no cable television. And in no cable television, 70% are retained, 15% switches to A, and 15% to Company B. Same as second represent Company B, and the third has represent to no cable. So we have this tree diagram that helps us to understand what is the matrix B look like. Using that diagram, it is easy for us to prepare the transition matrix and also the state matrix has given. So from A to B and no cable, so we prepare a transition matrix or transition property matrix, and then the state matrix X is 15,000 currently in A, 20,000 are in B, and the remaining are in no cable TV. Example 2. A continuation of a consumer preference in example 2. So to find the state matrix representing the population in three states, after 1 year, we have to multiply P by X. So thus, Px gives us 23,250 subscribers in Company A. 28,750 subscribers in Company B. One of the appeals of this matrix solution is that once the model has been created, it becomes easy to find the state matrix, representing future use by repeating to multiply the matrix B. So let us see the process here. So Px is all the given, since the matrix stands and the transition properties the same for the first year to the third year. We can find after 3 years. We have P raised to p raised to 3x. So after 2 years, we are not p squared. It is p cubed x in this case. After 3 years, Company A will have 30,283 subscribers. Company B will have 39,042 subscribers. If we are trying to find after 5 years, we have to find p raised to 5x, so the number of subscribers are after 5 years. In Company A, 32,411 subscribers. In Company B, 48,812 subscribers. And if it is after 10 years, we need to find p to the 10th or p raised to 10x. So Company A will have 33,287 subscribers. B will have 47,147 and the remaining is in no cable. Now, if you continue this process, then the number of subscribers eventually reach the steady state. That is, as long as the matrix P doesn't change. The matrix product P raised to nx approaches to limit x bar. In this particular example, the limit is the steady state matrix. We can easily get this result using a graphing calculator. We can prepare the table and we can see p raised to 10x. So you can find p raised to 11x, to 12x. If we have to 13th and 14th, it looks like that this is third state and we take as x bar 33,333 in A, 47,619 in B, and 19,048 in no cable television. Now, if we want to prove that this is 13th state, we can easily check this result by saying that this x bar satisfy this result. P, or the probability of x bar to x bar, this after getting this x bar, if 1 multiplied by p, that rally must be still the same. Yes, we have finding the p, or the probability of x bar, the same as the x bar. Hence, this x bar reaches 33,333 in Company A, 47,619 in Company B, and 19,048 in no cable TV. Cryptography. A cryptogram is a message written according to a secret code. The Greek word cryptos means hidden. This section describes a method of using matrix multiplication to encode and decode messages. Begin by assigning a number to each letter in the alphabet, with 0 assigned to blank space as follows. 1 equals A, 2 is to B, and so forth until you reach 26 to Z. Then, the message is converted to numbers and partitioned into uncoded row matrices, each having n entries, as demonstrated in example 4. So next, example 4, forming encoded row matrices. Write the encoded row matrices of size 1 by 3 for the message Meet Me Monday. Partitioning message, including blank spaces, ignoring punctuation, into groups of 3 produces of the following encoded row matrices. We already know the assigned number for a letter. So, meet me Monday is 13 for M, 5 for E, T for E, 20 for T, 0 for the spaces, M for 13, 5 is for E, 0 for space, 13 is for M, 15 is for O, 14 is for N, 4 is for D, 1 is for A, 25 is for Y, 0 is for the blank space. Note that the blank space is used to fill out the last uncoded row matrix. So this is the step-by-step process. So we're gonna try the encoded 1x3 row messages for a matrix. So how we're gonna use the invertible matrix to encode the message meet me Monday. So in order to encode it, we're gonna do is multiply the uncoded matrices each one. So this is the uncoded row matrix to encoding matrix, which is 1 -1 1 -2 1 -1 2 3 and -4. So we're gonna have the work over here, and so we're gonna take 13 5 and 5, and then we're gonna multiply that to encoding matrix. So we have to the matrix multiplication, and then this is 13 times 1 plus 5 times -1 plus 5 times 1. Then we do it again to the second column. 13 times -2 plus 5 times 1 plus 5 times -1. And then we do for the third column. 13 times 2 plus 5 times 3 plus 5 times -4. And then you repeat to the next one, which is 20 0 and 13 multiply to encoding matrix. So we have 20 times 1 plus 0 times -1 plus 13 times 1. Then next we have 20 times -2 plus 0 times 1 plus 13 times -1. And lastly, we have 20 times 2 plus 0 times 3 plus 13 times -4. So by repeating it again, 2, 5, 0, and 13, we have 5 times 1 plus 0 times -1 plus 13 times 1. For the second column, 5 times -2 plus 0 times 1 plus 13 times -1. For the third column, we have 5 times 2 times 0 or 0 or plus 0 times 3 plus 13 times -4. And repeat it again to the uncoded row matrix. We have 15, 14, and 4. So for the first column, 15 times 1 plus 14 times -1 plus 4 times 1. For the second column, we have 15 times -2 plus 14 times -1 plus 4 times -1. And the last column, we have 15 times 2 plus 14 times 3 plus 4 times -4. And for the last uncoded row matrix, we have 1, 25, and 0. For the first column, we have 1 times 1 plus 25 times -1 plus 0 times -1. For the second column, we have 1 times -2 plus 25 times 1 plus 0 times -1. And the last column, we have 1 times 2 plus 25 times 3 plus 0 times -4. So next, after we do the step-by-step process of multiplying uncoded row matrix to encoding matrix, this is the answer that we get. The sequence of coded row matrices is 13, negative 26, 21, 33, negative 53, negative 12, 18, negative 23, 42, 5, negative 20, 56, negative 24, 23, and 77. And after that, you will take all the values in order because it is important. Finally, removing the brackets produces the cryptogram below. So again, we have 13, negative 26, 21, 33, negative 53, negative 12, 18, negative 23, negative 42, 5, negative 20, 56, negative 24, 23, and 77. So after we get the coded matrix, we are now going to find the inverse matrix. So this is the original matrix, which is 1, negative 1, 1, negative 2, 1, negative 1, 2, 3, and negative 4. So we all know that this is a 3 by 3 matrix. So the identity inverse is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And now we are going to perform the row operation. So I want this negative 1 to become 0, so this is the process. Row 1 plus row 2. Just copy the row 1 and row 3. So 1 plus negative 1 is 0. Negative 2 plus 1 is negative 1. So 2 plus 3 is 5. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And next, I want this positive 1 to become 0. So this is the process. Negative 1 times row 1 plus row 3. So just copy the row 1 and row 2. So negative 1 times 1 is negative 1 plus 1 is 0. So negative 1 times negative 2 is positive 2 plus negative 1 is 1. So negative 1 times 2 is negative 2 plus 4 is negative 6. So negative 1 times 1 is negative 1 plus 0 is negative 1. So negative 1 times 0 is 0 plus 0 is 0. So negative 1 times 0 is 0 plus 1 is 1. And now I want this negative 1 to become positive. So this is the process. Negative 1 times row 2. So just copy the row 1 and row 3. So negative 1 times 0 is just 0. So negative 1 times negative 1 is positive 1. Negative 1 times 5 is negative 5. Negative 1 times 1 is negative 1. Negative 1 times 1 is negative 1. Negative 1 times 0 is yes, negative 1 times 0 is 0. Okay, now I want this negative 2 to become 0. So this is the process. 2 times row 2 plus row 1. So just copy the row 2 and row 3. So 2 times 0 plus 1 is 1. So 2 times 1 is 2 plus negative 2 is 0. So 2 times negative 5 is negative 10 plus 2 is negative 8. So 2 times negative 1 is negative 2 plus 1 is negative 1. So 2 times negative 1 is negative 2 plus 0 is negative 2. So 2 times 0 is 0 plus 0 is 0. And next, I want this positive 1 to become 0. So this is the process. Negative 1 times row 2 plus row 3. So just copy the row 1 and row 2. So negative 1 times 0 is 0 plus 0 is 0. So negative 1 times positive 1 is negative 1 plus 1 is 0. So negative 1 times negative 5 is positive 5 plus negative 6 is negative 1. So negative 1 times negative 1 is positive 1 times negative 1 is 0. So negative 1 times negative 1 is positive 1 plus 0 is 1. So negative 1 times 0 is 0. So plus 1 is 3. So next, I want this negative 1 to become positive. So this is the process. Negative 1 times row 3. So just copy the row 1 and row 2. So negative 1 times 0 is 0. So negative 1 times 0 is 0. So negative 1 times negative 1 is positive 1. So negative 1 times 0 is 0. So negative 1 times 1 is negative 1. So, and last, negative 1 times negative 1, and the answer is negative 1. So next, I want this negative 8 to become 0. So this is the process. Negative 8 times row 3 plus row 1. So just copy the row 2 and row 3. So 8 times 0 is 0 plus 1 is 1. So 8 times 0 is 0 plus 0 is 0. So 8 times 1 is 8 plus negative 8 is 0. So 8 times 0 is 0 plus negative 1 is negative 1. So 8 times negative 1 is negative 8 plus 2 is negative 10. So 8 times negative 1 is 8 plus 0 is negative 8. And now, I want this negative 5 to become 0. So this is the process. 5 times row 3 plus row 2. So just copy the row 1 and row 2. So 8, correction, it is 5. So 5 times 0 is 0 plus 0 is 0. So 5 times 0 is 0 plus 1, 1. So 5 times 1 is 5 minus 5 is 0. So 5 times 0 is 0 plus negative 1 is negative 1. So 5 times negative 1 is negative 5 plus negative 1 is negative 6. So negative 5 times negative 1 is negative 5 plus 0 is negative 5. So that's it. We already find the inverse matrices. So this is the original matrix and this is the inverse matrix. So next, after getting the coded matrix and the inverse matrix, now we are going to decode the message. So we're gonna use the inverse and decode the cryptograph. So the next thing we do is since we have 3 by 3 matrix, then we're gonna do is 1 by 3 row matrices. So for example, if you're given a 2 by 2 matrix and you're gonna write a 1 by 2 matrices, in this case, we are going to do, or we are gonna put this up into groups of 3. After you do that, you're going to multiply this 13, negative 26, and 21 as a coded matrix, two inverse matrices, which is -1, -1, 0, -10, -6, -1, -8, -5, and -1. The row comes to 13 times -1 plus -26 times -1 plus 21 times 0. Then you repeat to the next column with 33 times -10 plus -53 times -6 plus -12 times 1, and do it again for the third column, which is 13 times -8 plus 26 times -5 plus 21 times -1, and repeat it again. So the next coded row or coded matrix is 33, -53, and -12. So -33 times -1 plus -53 times -1 plus -12 times 0. The second column is 33 times -10 plus -53 times -6 plus -12 times 1. And the third column is 33 times -8 plus -53 times -5 plus 12 times -1. Then the next coded metric is 18, -23, and -42. So 18 times -1 plus -23 times -1 plus -42 times 0. And the next column is 18 times -10 plus -23 times 6 plus -42 times 1. So the third column is -8 times 18 plus -23 times 5 plus -42 times -1. So the next decoded matrix is 5, -20, and 56. So 5 times -1 plus -20 plus or times -1 plus 56 times 0. So the second column is 5 times -10 plus -20 times -6 plus -56 times -1. So the third column is 5 times -8 plus -20 times -5 plus 56 times -1. And the last coded matrix is -24, 23, and 77. So -24 times -1 plus 23 times -1 plus 77 times 0. So the next row is -24 times -10 plus 23 plus -6 plus 77 times -1. And the last column is -24 times -8 plus 23 times -5 plus 77 times -1. So on the next slide, I will show you the answer. And now here at the example 6, decoding a message, I will show you the answer on the decoded row matrix, because we are done multiplying the coded row matrix to decoding matrix inverse. So this is the answer: 13, 5, 5, 20 0 13, 5 0 13, 15 14, and 4. And the last one is on the next slide, so we are going there. So here is the last answer. On the decoded row matrix, we have 1, 25, and 0. So the sequence of decoded row matrices is 13, 5, 5, 20, 0, 13, 5, 0, 13, 15, 4, 4, 1, 25, 0. And the message that we get is meet me Monday. So that's all. Thank you.